All right, let's finish with AP exam review number 3 on Riemann sums. This is 2007, number 5. The volume of a spherical hot balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function, r of time t, where t is measured in minutes. For time between 0 and 12, the graph of r is concave down. The table above gives selected values of the rate of change r prime of t of the radius of the balloon over the time interval from 0 to 12. The radius of the balloon is 30 feet when t is equal to 5, and we're given the volume formula, 4/3 pi r cubed. Part A, estimate the radius of the balloon when t is equal to 5.4 using the tangent line approximation at t equals 5. Is your estimate greater than or less than the true value? Give reasons for your answer. And if we first start off with trying to get the tangent line equation, well, let's first identify what our independent and dependent variables are. We have time as an independent, radius as a dependent, and we know that at time t equals 5 seconds, the radius is 30 feet. And so we also need to find the slope at this ordered pair. So we need to find r prime of 5. What is the rate of change of the radius at 5 seconds? And we look at our table here. The rate of change at 5 seconds is 2 feet per minute. That's given by r prime. So we have our slope, we have our ordered pair. We can write our tangent line equation. So instead of x and y, we're using t and r. So r minus 30 is equal to our slope, 2 times t minus 5. We solve for r. So 2 parentheses t minus 5 plus 30. And if we want to find the tangent line approximation, we simply plug in our decimal value into our tangent line equation. So we're trying to estimate when t is equal to 5.4 what the radius is going to be. So plug in 5.4, we get 5.4 minus 5, which is 0.4, times 2, which is 0.8, plus 30 is 30.8. Okay. Now, we know, let's see, it says, is your estimate greater than or less than a true value? Now, we know that our original radius function is going to be concave down. So we know that the original graph is going to be concave down. So it's concave down, but it's increasing because we know that the radius, r prime, keeps increasing. Now, it's going to be increasing, but it's going to be slowing down. The balloon keeps expanding, but it's going to be expanding at a rate that is gets slower and slower. And so we know our graph will look something like this, where the radius is increasing, but then the rate of its increase is going to start slowing down. So that's why we have concave down. Now, if we have a tangent line equation that is tangent, if we draw a line that is tangent to a curve that is increasing and concave down, then any point on that tangent line is going to be higher than the actual value on the graph. So if we can draw and just visually kind of convince ourselves that that's going to be the case. So if we have a tangent line for a curve that is increasing and concave down, we're going to get an over approximation since the tangent line will be above the curve. Okay, part B. Find the rate of change of volume with respect to time when t is equal to 5, indicate units of measure. So this is going to be a problem that involves related rates. So we're trying to find the rate of change of volume with respect to time. So we're trying to find dv over dt. And we're given v is equal to 4/3 pi r cubed at t equals to 5. We know that at t equals to 5, our rate of change, our radius is 2 feet per second. And we know that at time t equals 5, our radius is 30 feet. So based off of part A and as well as the table, we can gather all these pieces of information that we can plug in once we find the derivative with respect to time for velocity. For volume. So we find the derivative of each variable with respect to time. So the derivative of v is 1, but then we attach dv over dt. 4/3 pi is just a coefficient, so that's just going to attach itself to whatever our derivative is. R cubed, the derivative for r cubed is 3r squared, but then we're trying to find the derivative with respect to time for each variable, so we have to attach a d over dt for radius, so we attach dr over dt. So this is our result of our derivative of both variables with respect to time. So v becomes dv dt, r becomes dr dt, and then we have 3r squared. So the 3's cancel out. We're left with 4 pi r squared times dr dt. And we have all these information that we can plug in from what we've gathered to find dv dt. So 4 pi r squared gets replaced with 30 squared. Dr dt gets replaced with 2. And we can simply plug in our calculator and work this through. We get 7,200 pi cubic feet per minute. Okay. Part C, use a right Riemann sum with 5 subintervals indicated by the data to approximate the definite integral of r prime of t from 0 to 12. Using correct units, explain the meaning of the definite integral of r prime of t from 0 to 12 in terms of the radius of the balloon. And right Riemann sum, we are going to be finding the width and the appropriate height for each of the rectangles that we're going to be adding up. So we can go back to our table. Okay, 5 subintervals. So we have one interval here, 2, 3, 4, 5. And the first interval has a width of 2, and the height, we want to choose the right endpoint height for each rectangle, because we were using right Riemann sum. So it will be 2 times 4, and the second rectangle will be 3 times 2, because 5 minus 2 is 3. The third rectangle, 7 minus 5 is 2, and then between these two, we're choosing the right endpoint, 1.2. That's the height. The fourth one, 11 minus 7 is 4. 4 times 0.6. And finally, 12 minus 11 is 1. 1 times 0.5. So we're just doing width times height for each of the rectangles, and we're choosing the appropriate right upper corner for each of our rectangles. So when we total that up, we're going to get 19.3 feet. And so this Riemann sum represents the estimation of the radius of the balloon growth in the first 12 minutes. So the accumulation of the rate of change of the radius size will just be the accumulation of the radius size, which is that 19.3 feet represents how much the balloon grew from 0 to 12 minutes. Okay, part D, is your approximation in part C greater than or less than the actual value of the definite integral of r prime of t from 0 to 12? Give a reason for your answer. Now, if we're looking at this graph, if we were to graph to this these ordered pairs, we see that the y value, this r prime, is decreasing. So if we have a decreasing graph and we're doing right Riemann sum estimation, we see that if we're drawing this for a decreasing function, we're going to get gaps below the graph. So we know that if we add up these rectangles, it's going to be less than the actual area under this curve, because we see these gaps that are not accounted for. So because of that, since r prime is decreasing and we're using right Riemann sum approximation, visually you can tell to convince yourself, and we know that this will be an under approximation from the actual area under this curve.